We've been talking about applications of the Bronsted acid-base theory, but I do want to talk about in this section before we leave what's called a Lewis acid and Lewis base, or the Lewis acid-base theory. In this diagram, all right, there's lots of things going on, all right. We have in the middle here, we have some intramolecular forces. Those are covalent bonds that happen between atoms, and they're very strong. We also have up here in these little dotted areas, if you remember from Chem 222, those are intramolecular forces, forces between the molecules. Those are hydrogen bonds. The red atoms are oxygen and the whites are hydrogen. Those are the hydrogen bonds. But what I want to focus on is what's happening in the middle of the atom. And you can see there's like an arrow pushing on the middle. Now the middle atom is a metal. I think it's nickel. And what's happening here is a lone pair on the blue atoms, which is what the blue atoms are, the nitrogens. The lone pair on those is pushing electrons into that metal center. And this is a different kind of an interaction than we've seen so far. And understanding this has cool implications for the stuff we're going to learn. And Lewis was the person that kind of pulled this together, the same Lewis of Lewis structures, by the way. So let's check out more about what that lone pair pushing itself into a metal is all about, and why you might use an arrow there instead of like a regular bond or a dotted line for the IM forces from Chem 222. To understand Lewis acid and base theory, we need to define first what a Lewis acid is and what a Lewis base is. A Lewis acid is an electron pair acceptor. It's some kind of an atom that can accept a lone pair of electrons in it. So in order to have a lone pair accepted, you must have an empty orbital. And boron trifluoride is the classic Lewis acid. Boron is one of the group 3A twisted metals. I've called them twisted metals since Chem 221, and now you'll finally see why. That empty 2p orbital on boron is kind of sticking out above and below the trigonal planar boron molecule right there. It's an empty orbital, doesn't have any electrons in it. That's going to be a good place to accept a lone pair of electrons. Ammonia, NH3, is a classic Lewis base. Ammonia, like most things with nitrogen, has a lone pair on the nitrogen. So I'm going to draw the lone pair in right there, but you can see that that should be on the molecule rotating. That should be a tetrahedral electron pair geometry. It's a trigonal pyramid molecular geometry. That missing little part at the top of the tetrahedron is where that invisible lone pair is. So ammonia is considered a Lewis base. It's going to be able to donate its electron pair into a Lewis acid, into some kind of atom that can accept those lone pairs of electrons. When you have a Lewis base donating its electrons to an empty orbital in a Lewis acid, you create what's called a coordinate covalent bond. It is a bond that where electrons are being shared, covalent bonds, but all of the electrons come from one atom, and this is different. So in boron trifluoride right there, each of those BF bonds is a regular covalent bond because one electron is coming from boron and one electron is, if you will, coming from fluorine. In a coordinate covalent bond, both electrons come from the same atom, and they push themselves into the empty orbital of the Lewis acid.
Boron trifluoride is a Lewis acid because it has a deficiency of electrons. Ammonia acts as a Lewis base by donating its lone pair of electrons into BF3's vacant valence orbital. The product of this Lewis acid-base reaction is a single molecule with a new bond, called a coordinate covalent bond, because both the electrons for the bond come from only one species.
Sometimes in pictures, the coordinate covalent bonds are listed with an arrow like that. It's trying to show that both electrons come from one atom. You do go from a trigonal planar boron to a tetrahedral-like boron. All right, it does actually affect the geometry. The Vesper rules we looked at in Chem 222 were all about electrons being repelled. Now this boron has an extra set of electrons in that orbital, which changes all the geometry and stuff like that. So this is a type of an acid-base theory. Now, in Bronsted acids and Bronsted bases, the acids were hydrogen donators and the bases were hydrogen acceptors. In Lewis acids and bases, you have to have some kind of empty orbital where electrons can be accepted, and the bases will have lone pairs where electrons can be donated. And believe it or not, Bronsted acids and bases can be seen as a subset of the Lewis acid-base theory. So here's like an H plus reacting with water to make hydronium. Well, H plus is the acid. It's missing lone pair, doesn't have electrons. Water, on the other hand, definitely has lone pair electrons. It pushes its lone pairs into the H plus, if you will, to make the H3O plus hydronium ion. Sometimes they call these adducts, a Lewis acid, Lewis base adduct. That just means the Lewis acid and Lewis bases come together. Ammonium from ammonia is the same thing. Ammonia is the Lewis base. It's reacting with the Lewis acid H plus to make ammonium. Notice here that Lewis bases must have lone pairs, all right? You can't have a Lewis base if it doesn't have any lone pairs on it. So without a lone pair, you're kind of out. Nitrogen, oxygen, a lot of the halogens like chlorine are great Lewis bases. On the other hand, the Lewis acids are going to be places where you can put electrons. Hydrogen is obviously a good one here. Aluminum and boron are great ones. And we're going to see almost all the transition metals have empty orbitals on them where you can push electron density into. This question says, which of the following is a Lewis acid? Okay, now a Lewis acid has to have something where lone pairs can be placed in. If you have a molecule with a lone pair of electrons, it'll be more likely a Lewis base. So for example, on the first one right there, which is methylamine, nitrogen, if you draw the Lewis structure out, nitrogen has a lone pair. That's going to be more likely a Lewis base. If you draw carbon monoxide out, and this would be good practice if you haven't done a Lewis structure for a while, carbon monoxide has a triple bond, but there's a lone pair on both the carbon and the oxygen. That's not going to be a good, that's going to be more like a Lewis base, not a Lewis acid. Hypochlorite there, the last one, if you draw out, or the next to last one, has a Lewis structure where there's a single bond between the chlorine and the oxygen. The chlorine has a filled octet, and so does the oxygen, but notice lots of lone pairs, all right? Lone pairs, again, better Lewis bases than acids. So most of the transition metals, like silver in answer B, are going to be great Lewis acids. Lewis acids are usually transition metals or the group 3A metals, like boron, aluminum, gallium. It can be the hydrogen ion too. So just kind of keep that in the back of your mind. This ability of transition metals to be Lewis acids makes most of their solutions in water acidic, and we're going to see that here in a little bit. A complex ion, which is something we'll talk about in the Le Chatelier's principle, a complex ion then is usually some kind of metal center with Lewis bases around it. And complex ions can be really, really stable. So in the pictures here on the right-hand side, the central atom is going to be some kind of probably Lewis acid. The lower one there is definitely copper. The upper one could be cobalt, it could be chromium, all kinds of things. But anyway, in the top one up there, you can see those are actually water molecules. The red atoms are oxygens, and the little white ones are hydrogens. And those waters are pushing their lone pairs into the transition metal center. The lower picture, it's ammonia. So the blue atoms are nitrogen, and they're pushing those arrows right there, their electrons into that copper center to make these complex ions. All metal ions form complex ions with water, like the one up there on the top. And the number of water molecules, will vary. So X is the number of water molecules, is usually between 4 and 6, all right? So some transition metals will have just 4 waters around them, some will have 6. We don't need to worry about that in this class, but they will form these complex ions. And complex ions have huge implications for the reaction in a chemistry lab.
In the test tube is a solution of copper sulfate. When we add a few drops of ammonia, the ammonia acts as a Bronsted base and causes the precipitation of solid copper 2 hydroxide. The solution turns a cloudy blue. If we then add a much larger amount of ammonia, the solution turns a very dark blue. The precipitate dissolves upon direct reaction with ammonia molecules. The ammonia has donated its electrons to the copper ion, and so now acts as a Lewis base. Ammonia is a Bronsted base and produces hydroxide ion in solution that can lead to formation of solid copper-2 hydroxide. With additional ammonia, a Lewis acid-base reaction occurs.
So this is kind of cool. Imagine you're a scientist and you're studying copper, and copper in water has kind of a light blue kind of a color, like the lower part of that beaker right there. And you add a little bit of ammonia. Now ammonia is a weak base and it does create some hydroxide. So the first thing that you see is kind of a solid, all right, it's kind of a blue-white solid, and that's copper-2 hydroxide, an insoluble compound. And copper-2 hydroxide you can precipitate out, you can filter it, whatever, and get it. But let's say you're like, man, I got to make a lot of copper-2 hydroxide. So you add excess ammonia. Well, all of a sudden then your copper-2 hydroxide solid goes away and you end up with this wild dark blue solution. Well, this dark blue thing is a complex ion, and this is just the effects. Like sometimes people will say like, hey, if I made, if I had 1 mole, I get the solid. If I had 2 moles, I'll get more solid. No, that doesn't always work out, because sometimes complex ion equilibria kicks in and you end up dissolving your solids. So in the beaker on the left, the lower copper solution, that's actually copper surrounded by water molecules. So waters are acting as the Lewis bases and copper is the Lewis acid. The waters are displaced by a little hydroxide because copper-2 hydroxide is pretty insoluble, but you keep adding extra ammonia. Ammonia actually kicks the hydroxides out, and you end up with the complex ion CuNH3 4 to the 2 plus, which is that cool dark blue thing. Very, very wild. This really stumped scientists for a long time, like what the heck was happening? And so complex ion formation is the answer here. And these are all just Lewis bases reacting with a Lewis acid. The Lewis acid is almost always a transition metal, and the Lewis bases, again, will be things like water, ammonia, hydroxide, stuff like that. Just depends on which one you've got. So there's some really interesting chemistry that happens in the Lewis acid base arena when it comes to transition metal.
Oxygen binds weakly to the iron ion at the center of a heme group in the hemoglobin molecule. In an oxygen-poor area of the body, the O2 is easily removed. Carbon monoxide, in contrast, binds very tightly to the iron and is very difficult to remove. The presence of carbon monoxide makes it impossible for the blood to transport oxygen effectively.
Thank heavens for these Lewis acid-base adducts, because without that, we wouldn't be able to breathe. Oxygen coming into our bodies is attracted to the iron in heme in our blood. It has a weak bond. It goes then to somewhere where the oxygen is needed, and because it's a weak bond, the oxygen can be kicked out. So it gets oxygen to the places in our body that needs it. On the other hand, carbon monoxide is another thing that makes a Lewis acid-Lewis base interaction with the iron. Unlike oxygen, though, that's a pretty strong reaction, and it's harder to dislodge the CO. That's what causes people to die and stuff when there's carbon monoxide poisoning. If you have a carbon monoxide detector, of course, it's a good thing. It'll detect it, stuff like that. Complex ions will undergo what's called hydrolysis to give these acidic solutions. So we saw earlier that most transition metals have lots of waters around them. Well, some of the waters around the metal can break down a little bit. This is an example with copper. All right, copper with 4 waters around it can react with water. It makes copper with 3 waters and then a hydroxide. And notice your positive 2 goes to a positive 1 because hydroxide's negative 1. But one of the H's in the hydrolysis is kicked out as hydronium. Now this is a Ka expression. Remember here that in a Ka you have some kind of weak acid plus water, water. It makes the conjugate base, which is that weird thing, and hydronium. So this has a Ka. It's a hydronium creator. You could think about this as equilibrium. If you want, you could put the other arrow back because they're going to be small. But this also explains why transition metals in water almost always acidic, all right? This hydrolysis process, water is pulling one of the H pluses from this complex ion, and it makes a little bit of an acidic solution. It's not like HCl acidic by any means. It's a weak acid, but it is enough to be measurable, and that's kind of important. So the question is, will a 0.1 molar iron 3 chloride solution have a pH which is, and then there's the three possibilities. Okay, chloride is the conjugate of a strong acid, HCl. So chloride doesn't affect anything. But iron, a transition metal like we just saw, is a great Lewis acid. And those Lewis acids will a lot of times create hydrolysis, which will create a slightly acidic solution. That's going to make our pH less than 7. Transition metals will usually make solutions which are a little bit acidic, and that's kind of an interesting thing. So make sure you know where the transition metals are on the periodic table, stuff like that. The main group metals don't do this. So like magnesium and calcium, potassium, they don't do the hydrolysis thing like the transition metals do. It's only the transition metals which seem to do this. This leads us to the idea of amphoteric systems. An amphoteric system is just a system that can act as both an acid and a base. And if you know about Lewis acids and Lewis bases, you'll be able to see why. Now, we've already seen that water is amphoteric. It can act as both an acid and a base, but there's a lot more than that. Aluminum is a great example of an amphoteric atom. In this case, aluminum hydroxide, it's reacting with H+. The H+ is reacting with hydroxides to make water. You end up with Al3+. In this case, aluminum hydroxide is acting as a Bronsted base. All right, the hydroxide is accepting the H+ to make water. Aluminum's kicked out. So this case, aluminum hydroxide is acting as a Bronsted base. However, the same aluminum hydroxide can, in excess hydroxide situations, create the complex ion AlOH4-1. Now in this one, aluminum hydroxide with its group 3A twisted metal does have an unused 3p orbital. And that 3p orbital can have electrons pushed in it from a hydroxide. So hydroxide in the second example is the Lewis base, and aluminum hydroxide is acting as a Lewis acid. Electrons are being pushed inside it to make this complex ion, to make this Lewis acid, Lewis base adduct. So wow, aluminum hydroxide can be an acid and a base, just like we've seen water can act as an acid and a base. There are several examples of these compounds that go back and forth. This picture shows in a little bit greater detail what's happening. In the first one, we have just aluminum plus 3, and that's just a clear solution, no big deal. You add some ammonia, all right, and the ammonia is a hydroxide creator, so you end up making AlOH3, and that's a fairly insoluble compound, so you can see it's kind of white right there. Well, if you add extra hydroxide, all right, and if you add sodium hydroxide, this would definitely do it, the white solid goes away. And that's because in this case now, you've got the complex ion, the AlOH4-1. Ions by themselves do not show up as precipitates. They would dissolve into the solution. They may have a color, but they're not going to make any solids. So in this case, AlOH4-, you would definitely see the solid just go away. There'd be nothing left over. On the other hand, if you start with aluminum hydroxide there and you add HCl, now aluminum hydroxide is acting as a base. HCl is the acid, Bronsted base. All of this stuff will dissolve. You'll end up making water. So this stuff then begins to dissolve. All right, over here then there's nothing left over. Aluminum chloride, the product there, would be water soluble. You shouldn't see anything. So again, this is acting as both an acid and a base. Complex ions are very stable, like we talked about, and they baffled scientists for a long time. You can have an equilibrium constant for a formation, for a complex ion. It's called a formation constant. It's given the symbol K sub F. If you have a Kf expression, then how to build it? The complex ion is the product. So in this case, if we wanted to have a Kf expression for this reaction, CuNH3 4 2+ would be the product. And anything that goes into making the complex ion will be the reactants. So in order to make that CuNH3 4 2+, you would need a copper and 4 ammonias. So the Kf expressions look a little weird, but they're always products divided by reactants, just as before. Nothing in this one is a solid or liquid, so you'd have CuNH3 4 2+ on the top, and you'd have copper 2+ and ammonia to the 4th power on the bottom. Kf values are usually very, very product favored, very, very big numbers, much larger than 1. And that just indicates that they're very product favored. So with the Kf this large, you know that the CuNH3 4 2+ is going to form if it's given the right stimulus. Very product favored means very likely to form, and formation constants are usually very product favored. This is an example with some practical uses. Silver chloride is pretty insoluble, and getting silver chloride off glassware sometimes can be tough because it sticks on there. But if you add ammonia to the silver chloride, you end up making a complex ion, a silver with 2 ammonias, and the chloride falls off. And this is a great way sometimes to dissolve silver chloride, which just doesn't want to go away. So you can use this complex ion to actually help you get the stain off some silver chloride glassware. There's a type of an equilibrium constant for silver chloride going to silver plus and chloride. It's called a KSP, and we'll talk about that in a future lecture. But anyway, this K value, 1.8 times 10 to the minus 10. Don't worry about the KSP, but this is an equilibrium constant that's much less than 1. And that means you're going to have a lot of silver chloride and not hardly any silver plus or chloride. Well, we can combine this with a formation constant for this AgNH3 2+ thing we talked about earlier. And this formation constant is also very product favored, 1.6 times 10 to the 7th. So notice here we've got a K expression for silver chloride breaking into the ions. We have a formation constant for this complex ion thing. If you combine them, you can figure out the net reaction. And again, when you combine them, the silver ions cancel. You have silver chloride and 2 ammonias making AgNH3 2 plus chloride. This K is still reactant favored. It's less than 1, but it's not as reactant favored as the initial one was. So it's more likely that you'll get the silver chloride reacted with ammonia than you will just the silver chloride breaking down by itself. So this is really helpful again to scientists. Silver chloride can be really tough to get off glassware, but with a little ammonia, the complex ion is formed. You whoosh away the excess complex ion because AgNH3 2+ will dissolve in water. It's a good way to get rid of junk off your glassware.